Section 2.3 is Computations of Derivatives, and the highlight of the lesson is the power rule. We've actually got several basic derivative rules that we're going to talk through. So let's go through these, and there's one that's missing. I just used the ones in your book sort of outlined, and I either missed this one or it may not have outlined it as such. So I'm going to throw in one more in the middle of this. But the first one it actually talks about is if you have a function that's a constant. So like let's say it said f of x or y equals 5. What does y equal 5 look like? Horizontal is the word we want, right? It's I know you guys like the word straight. All lines are actually straight. Horizontal is what you mean. I know that's what you mean when you guys keep saying straight. It's a horizontal line. What can you tell me about the slope of a horizontal line? It's 0. So anytime you're working with finding a derivative of a simple number, plain old number, I don't care if the number says square root 7, it's a number, then its slope is 0. So the tangent line or the derivative is 0. Okay, so here's the one that's missing. This I'm going to write here is linear. Okay. So let's say you have the equation f of x equals, and we'll write it the way that you saw it way back when, mx plus b. This is a line, and we saw the picture of this happen before, right? This is a straight line, but not a horizontal one, right? So it's a line like this. What is the slope or the tangent value? What is the derivative of the line? What is the slope of the line? M, right? It's part of the equation. The slope of a line is given as a part of its equation. It's M. So f prime of x, when you have a linear equation, is simply the coefficient in front of the x. And that's the picture we saw where the line became a horizontal line, didn't it? It was a constant horizontal line when we took the derivative. Power rule is different. Power rule, I'm going to write it down for you. But we actually saw an application of this when we did the graphing. When we were talking through it, Hannah identified for us that it looked like it was a cubic graph, right? So we saw something that looked like x cubed, and when we took the derivative, the graph looked like x squared. And then we saw a graph that looked like x squared, and when we took the derivative, it looked like x. So it looks like that the exponent simply goes down by 1, and that is exactly what's happening. However, it also has a constant multiplier in front of it that was the previous exponent. Now we couldn't see that happening because we weren't doing anything with scaling. We were just doing sketches, okay? But this is the power rule. If I have x to the n, it looks like the n comes down in front of the x, and we decrease the exponent by 1. This is the only, but I probably shouldn't say only, but this is what I believe is the only fact that my husband remembers from calculus when he took it. I don't know why, but this is the one people tend to remember. The next two are just simply interesting features that I'll show you when you use them, but when you use them, you won't realize you even used them because you just are sort of assuming that this is going to work, and it does. This one says that if I have a number, because that's what C is a constant multiplier number, in front of the function, then that number is simply part of the derivative, and we take the derivative of the function as though it doesn't really affect the C, because it doesn't. And like I said, I'll show you when you use it, but you're going to use it without even realizing it. The same thing happens down here. What we would like to be true is that there's a plus or a minus. We can simply take the individual pieces and put the plus or the minus back between them, and that's actually what we can do. And again, it's one of those things that when you do it, you're not even going to realize you did it, but you used a fact that had that feature. So we're going to practice through some of these. First of all, noticing here on problem number 1 that this uses that last feature. I've got these pluses and minuses between things. But that's good. I mean, that's fine. I'm just going to do them each individually and put the pluses and minuses where they were originally. Nothing's going to change on that. Now, there is one thing here that's weird that doesn't really look like any of those definitions. What about this doesn't really look like it fits in with what I did on the previous slide? That 4 over x. Is there a way we can rewrite this so that it actually looks like it might fit with those descriptions? Do you guys remember that? It's an important feature. When I have a value in the denominator, I can bring it up to the numerator if I change the exponent to be a negation, a negative. That's a property of exponents. So I know you've seen it probably in high school algebra is where you probably saw it. And then we can use that fact because now this looks like the power rule. Because that exponent is actually upstairs. The whole x is actually on the top of the function now. We don't have a denominator. All right, so let's take a look at how this actually works out. So I'm going to write y prime because the function started out y. The first one is x to the 7th. That's a power rule. So x to the 7th will become what? X to the 6th. What else? We're missing something. 7 in front. Thank you. So I have 7x to the 6th. So the 7 looks like it comes down in front, and then the exponent decreases by 1. Now there's a plus sign, so we'll include the plus sign. The term in the middle says 3x. That's that linear rule over here that I sort of added in on the top corner because we think about it a little bit differently anyway than the power rule. It actually is an application of the power rule, but we think about it differently. 3x, what's the derivative? 3, because we're actually talking about slope. So the reason that's the x derivative is because that's the slope of 3x is 3. Now that 4x minus 1, well, we're going to take the negative 1 and we're going to bring it down. And we're actually going to take the negative 1 and we're going to multiply it by a negative 4. There's a negative in front and I now have a 4. So, in fact, you know what? Let me write it out a little bit differently than what I just said. Some of you have done this before, so you don't have to show this. I'm fine with that. But in case you haven't seen this before, it might be helpful. So I've got that negative 4 already written because I had a negative here and I have a 4 here. So there's the negative 4. And I took the negative 1 and I brought it down. And I'm going to write an x. And what's going to be the exponent on the x now? Negative 2. We decrease the exponent by 1, so this becomes negative 2. Okay, we're going to do one step where we clean this up a little bit. The first two pieces, there's nothing to clean up. However, on this one, I've got negative 4 times negative 1, which is 4, right? So we've got a positive. And this x to the negative 2 can be put back down in the denominator, right, so that it doesn't have a negative exponent and be written as 4 over x squared. A lot of pieces there. But you know what's not there? H's and limits. Right? If you were to work this out by hand, number 1, I really don't think you want to do x plus h to the 7th power. That's probably not high on your to-do list for the weekend. The rest of it wouldn't be awful, but that x to the 7th would take you a while. So I had Shannon in my office, and we were talking about, she was showing her homework, the limit stuff you guys just did, to someone else who's taken calculus before, and they said, why are you doing it that way? So I kind of thought it would probably be worth mentioning that the reason we have these rules over here is because if you use the limit definition like you saw it used in the last two sections enough, you start to notice patterns. And the patterns that come about prove that these rules work. And that's the deal. That limit definition is actually what proves that you can now do a shortcut to finding derivatives. Let's try another one. What about this one looks different? It's factored, right? Yeah, this looks kind of weird. And if you go back here on this list of basic derivative rules, there's nothing on here that says what to do when you have a multiplication of things, right? We'll get to that in the next section, but that's not present on this particular slide. So what are we going to do in order to use the rules that we currently have? We're going to distribute. We're going to FOIL, exactly. So the first thing we're going to do, and make sure you're very clearly labeling things, this function is not the derivative function. This is the original function multiplied out. So this is g of x that I'm writing down. And I'm going to FOIL this out, or I'm going to distribute this out. So I'm going to take x times 3x squared. That's 3x cubed. I'm going to take the x times the negative 4. That's negative 4x. Then I'm going to take the 1 times the 3x squared. That's 3x squared. And 1 times the negative 4 is negative 4. Are we happy enough with that? None of those terms combine. If they did, we would want to combine them because it would make the next step just a little bit quicker. They're not really in order of decreasing exponent, so you could do that if it bothered you, but you don't have to. It's fine to leave it like this. Because from this form I can do that derivative. I can find g prime of x. All right. So this is the constant multiplier stuff that I told you. You're going to do it without even realizing. I know this exponent's a 3 and I want to bring the 3 down, right? But when I bring the 3 down, eventually I'm going to multiply by the 3 that's already there, because that 3, a constant multiplier, stays as a part of the problem. So I'm going to take 3 times 3, and I'm going to get 9. And what will the new exponent be? Squared. It'll be a 2. All right, the middle term, or the first middle term, is negative 4x. What will that become? Negative 4, right? 3x squared. That's 6x. That's an application of that power rule and constant multiplier rule again. And then how about the derivative of the negative 4? That's 0. If you want to write it to show yourself a few times or whatever, that'd be fine. But you don't have to. You can just leave it off, and you're done. Is that good? Any idea what in the world that notation means? Because we haven't talked about it yet. d2f over dx2. It almost feels like I said something out of Star Wars, R2D2, I don't know, something. This notation is second derivative notation. Okay? So this means second derivative. What it means is I'm going to take the derivative, like I did in the last problem. I'm going to get an answer, and then what do you think I'm going to do after that? Do it again. I'm going to take a derivative of the derivative. Okay? The way that we read this notation, just so that you're aware, is this is the second derivative of f with respect to x twice. It's not my favorite notation. I would much prefer that we just did this. And this is the second derivative notation with primes. You just do double primes. Okay. Now I'm going to stick with the notation that they used because I don't want you guys to be scared of it or anything. But it isn't my favorite notation. The first derivative then will be df dx. All right, so here's our f of x function. It starts out x to the 6th. What is the derivative of x to the 6th? Perfect. 6x to the 5th. You guys are on track. Fabulous. Now the second one over here, that does not look like anything that we've done yet. And if you remember, the whole point in this section is that I'm able to change things into things that look like powers. So do you remember how to change a 5th root of x into something that looks like a power? X to the 1/5. You guys do remember. Very good. So this is x to the 1/5. And now I can use the power rule. So the power rule then would say that what's my derivative? 1/5. How do we get that new exponent? What is it? It is. Very good. -4/5. So we take the exponent 1/5 and we subtract the number 1 and we get -4/5. Okay, it's fraction subtraction. I know it's something you guys can handle. Okay, that's the first derivative. Let's take the second derivative and then we'll stop for today. So this is d2f dx2. It's easiest to take it from the point of view that we're currently at. What is the derivative of 6x to the 5th? 30x to the, what was that? 4th. Perfect. Now I have to take the derivative of 1/5 x to the -4/5. What will that be? -4 over what? 25. X to the what? Great job. -9 over 5. You got it. I am perfectly fine with you leaving this problem this way. I do want you to recognize how else it might look, for instance, if you were working in the back of a book or checking your answer. The first part's, of course, the same, but this actually might look like this. They might take this negative and make it down in the denominator, and they might change that 9/5 back into a 5th root because the problem started out as a 5th root. So you might actually see it written something like this, the 5th root of x to the 9th. I don't care that you actually do that on this. That's not a high list of, it's really just not high on my list of your priorities, but you might check an answer and come across something like that.